Oh, it's time to start. My name is Stratis Kardanelis, and I'm the chair of the e-YEG group. Welcome everyone to the 10th series of e-YEG webinars with invited presentations from Professor Jordi Corominas and Dr. Anika Braun. We would like to thank you for being here, and by initiating this session, I would like to welcome Professor Corominas, who is going to be our first speaker. I will provide a small introduction on his presentation and his background. Professor Jordi Corominas has a bachelor degree and PhD degree in geology from the University of Barcelona in Spain. In 1978, he joined the Department of Geotechnical Engineering and Geosciences of the Universitat Politècnica de Catalunya, Barcelona Tech. Currently, he is emeritus professor, visiting scholar at the Imperial College in UK in 1985 and at the University of Colorado at Boulder, US in 1993 and 1994. His research has focused on natural hazards and particularly on landslide hazard assessment and quantitative risk analysis. He has been former president of the European Center for Geomorphological Hazards of the Council of Europe in Strasbourg, France. He has been also a core member of the Joint Technical Committee JTC1. He has been awarded with the Barnes Medal by the International Consortium on Landslides, and he has delivered many lectures for Laram School, for New Zealand Geotechnical Society, but also recently for the International Symposium on Landslides in Cartagena, Colombia. We're really pleased to have Professor Corominas today with us. Please, Professor, turn on your camera and the space is yours.
Thank you very much, Stratis. I will try to share my screen.
In a moment. I think now you're able to do that. Yeah.
Can you see it?
Yeah. Sure. Now you're in full screen.
Okay. Thank you very much. It's really a pleasure just to deliver this talk here with this audience. I want to say that my presentation, in fact, is the work of is a collective work that has been performed through several research projects, rock models and georisk. So what I'm going to present is the work of myself, but also of my colleagues. We would like to share our thoughts and our point of view on fragmentation of rockfalls. Fragmentation of rockfalls is something that everybody knows, but very few research group has dealt with. And so the last years we were interested in knowing how is fragmentation working, and also try to work with fragmentation in our analysis, and particularly when we are interested in quantitative risk analysis. This is the outline of my presentation. I would like first to remind a few rockfall terms, then to explain a few tools that we are currently using, tools that are quite recent and has changed everything in our work, and then to visit what are the parameters that characterize fragmentation, and following this to present two models we have developed: a rockfall fractal fragmentation model and rockfall propagation model, or GIS. And then to present the capabilities of this model with an example concerning on quantitative risk analysis. Okay, I think we all know what a rockfall is. Rockfall is characterized basically by the free fall and then subsequent bouncing, rolling, and sliding. In principle, that rockfalls have no interaction with other particles, only with the ground. And what happens is, in reality, many rockfalls fragment, break, and then this is why Evans and Hunger in 1988, they proposed this term of fragmental rockfalls, in which they describe rockfall that the individual fragments move independently as a rigid bodies. They have little interaction among them. And they propose that fragmental rockfall involve volumes up to 100,000 cubic meters. I would say in practice, we talk about few thousand or few tens of thousands of cubic meters for fragmental rockfalls. There is another rockfall. It is a rock mass fall when a big event occurs. Then it's almost unavoidable not to have interaction between particles. Even though this interaction may be weak, you have impacts among the particles, and you may start noticing a kind of fluidification and development of internal pressures. These type of events that typically may affect rockfall up to hundreds of thousands of cubic meters. And finally, you may end up with rock avalanche. Rock avalanche is characterized by the rapid disintegration of the rock mass. And the main feature is propagates as a dry granular flow. Sometimes has been described as a turbulent grain flow with dispersive stresses. And rock avalanches have some specificities and some particularities. For instance, there are some textural features like reverse grading that we observe in some of the events in which the large particles are on top of the deposit or crashing of the grains. There are some features that characterize rock avalanche that we cannot see in rockfalls. Something I would like to say is that the path from rockfalls to rock mass flow to rock avalanches sometimes is progressive, and sometimes in some events we share different mechanisms inside the event. But I want to say that it's not a matter of size. So if we say that something is a rock avalanche or is a rockfall, it's not a matter of size, because there are events of tens of thousands of cubic meters that they maybe have a rock avalanche, and instead we have events of millions of cubic meters that they maybe have a rockfall or fragmental rockfall. This is the case of Randa, in which two events took place in a very short time period, 20 and 10 million cubic meters respectively. But this is not considered a rock avalanche, because this granular flow did not take place. And if we look at in detail to the deposit, what we see is that larger fragments they roll or they move up to the end of the deposit. We have a particle segregation with the small or the fine particles close to the apex of this fan, and large particles at the bottom. This is a feature typically from rockfalls, not for rock avalanches. So, well, this is something to keep in mind. Now, luckily, we have new tools. On the right, this is a picture when I was doing my PhD. I was just measuring with a tape and with a compass. In this case, the scar of a wedge failure, trying to obtain the dimensions, trying to obtain the involved planes. It took me several hours to get information of a tiny outcrop. But nowadays, we have tools like the LiDAR, the terrestrial laser scanner, in which we can obtain very easily, very rapidly, a point cloud. From this point cloud, we may derive discontinuities, we may obtain deformation, we may obtain digital surface models, and so on. So this work I did in several hours can be replaced by work much more efficient, like this. This is a large rock outcrop of maybe more than 1 kilometer width and 500 meter high. And this this outcrop may be characterized in half a day or 1 day, just to take all the information from this outcrop with a terrestrial laser scanner. And from this point cloud, we may obtain the discontinuities. And these discontinuities may be treated classically, as we do with stereographic projection or whatever. So the work we used to do in some days just to deal with this large outcrop, it would take us weeks or even months just to characterize this outcrop. Now we can do this very rapidly, very easily with these new tools. Another tool, very interesting, is the unmanned aerial vehicles and the digital photogrammetry, that with a drone, we may take images of the outcrops and then identify things that we can not see a bare eye from the bottom, see open cracks, see menacing blocks, and so on. And also we may identify that discontinuity surfaces, joint planes, and also, if we like, we may start assessing the volume of this menacing block, assuming different hypotheses, whether we consider only this small joint or this joint or this joint. So we may define different volumes. So you may obtain information that is really hard to do when we try to work in situ in the field. And also in this is an example of obtaining the dimension, the size of a recent failure. This is on the left, top left, the image of the before this rockfall, and on the bottom the image after the rockfall event. Just by subtracting superficial models, digital superficial models, we may obtain the size of the event. So this is something we can do very precisely and very rapidly. And this has changed the capabilities of the rockfall analysis. Well, let's go to the fragmented rockfalls. What characterizes the fragmented rockfalls is the rock mass splits apart, breaks, or disaggregates in the pre-existing blocks or form new blocks by breakage. And this means that the mass is redistributed, and also the energies, and also some characteristics is also the divergence of the trajectories of the blocks. So instead of following a given path, we may observe different trajectories of the following blocks. Well, we're going to discuss the fragmentation process and how we can characterize, and then how can we model it. Let's start first with the metrics, because how we describe fragmentation. There are different ways to describe fragmentation. From mining industry, they have a lot of work done about description of the fragmentation. But well, I would say that there are two parameters that characterize fragmentation. The first is the size of the largest block, but also we need to know what is the volume distribution of the fragments, not only the size of the larger block, but also the distribution of the fragments. I put here an example. These two blocks has been fragmented, but both have the same size of the maximum largest fragment. But however, we see visually that here we obtain two fragments, and instead here on the right, we have more fragments. So when we see the fragment distribution of these two blocks, this is in blue, the original block, and then in green, the fragment distribution is in case A, and in orange, the fragment distribution of the case B. So we see that these distributions are different. And one interesting thing is that if we start from the original surface of this block, that was in this case 4.5 square meters, then in the case A, we obtain 6.6, 50% of increase of the surface. But then in the second case, we double the original surface of the block. So we increase the amount of new surface area. How we characterize the the fragmentation, well, we started just going to the field, just doing an inventory of rockfalls and try to measure as much as possible all the blocks of the event. When the event was too large to measure all the blocks individually, we prepared sampling plots, we measured the plots, and we try to obtain the distribution of the whole event. Luckily, now we have other tools like, as I mentioned, the drones and the analysis of the photogrammetry, and then we may obtain the same distribution much easily, much faster, but from the orthophotographs, and just defining by hand the perimeter of these blocks, and also by using image software to obtain the distribution of these blocks. In this case is the block area, and you see here two examples of trying to obtain from these images to area distribution of the blocks. But we may also try to define a correlation between the area and volume of the block, and then we will obtain the rockfall or the volume distribution of this event. Going to the field, we finally observe that these distributions of fragments follow specific laws, particularly the tail of the distribution. As this is in a log-log plot, we may fit a linear relation. That means it follows a power law. So we observe that many rockfall events, they have the distribution of the fragments follow a power law that is a fractal behavior. And even though they look very, very close to each other, they look very, very similar. In fact, there is an important parameter, which is the slope of this power law that may be different from 0, in this case, from 0.5 up to more than 1. That means the distribution, they have a low value of the exponent, means that the proportion of the large fragment is bigger than in case we have a high exponent in which the proportion of the large fragments, these are the large fragments, and you see here the relative frequency is much lesser. So that's the exponent of this distribution give us an indication of what is the relative proportion between large fragments and small fragments. We also perform real scale tests by going to a quarry and then releasing blocks. And this is an image of a drone image from a block that has been released from a back actor. You see here how progressively the blocks breaks apart, and you see here how the fragments are displaced. Some of them, they move very fast, like a ejecta, and others they do more slowly. This is we have performed at least four tests. This is one the setting of one of the tests we perform. We just use different cameras, 3 cameras, just to obtain a stratigraphic a view, a 3D view of the trajectory of the blocks, and also we have the digital surface model of the blocks that were released, and also each block was painted with these color stripes, just in order to be checked, to be traced in the image of the video cameras. So here this is an example in which from the 3 different cameras we observe the same block, and this is the same point of the block as it is observed from the cameras. With all this information, with this treating these video images, we are able just to trace, to identify the center of mass, to reproduce trajectories, to estimate velocities, acceleration, impact angles, and then from all this information we may derive kinetic energies before and after the impact to obtain the coefficients of restitution, to estimate the energy balance, and so on. One thing we observe, for instance, is when the block fragments, and when we compare the rebound velocity of the block that they do not fragment with the block that fragments, we realize that the velocity of the rebound velocity of the blocks that do not fragment is smaller than the velocity of the fragments in the case that they fragment. So it's, well, this is in this experiment, this is test number 4, the rebound velocity of the blocks that do not fragment, it ranges between 4.5 meters per second to 6.2, but the fragments, they cover a wide range of velocities from 3 meters per second up to 15 meters per second. So fragments usually rebound faster than the blocks that do not fragment. And also, this is reflected by the fact that most of the small fragments, where they are deposited, they travel longer distances than the larger fragments. We also had the opportunity to observe, which is the cone that is formed by the fragments and the trajectories of the fragments. We may propose a kind of cone of fragments that defines the trajectories, that is also very wide, from 25 degrees to more than 150 degrees. So this is something that we know when we have a fragmentation, what could be the angle of the fragments may cover. And also with these experiments, we obtain as well the volume distribution of the fragment. So with all this information, we started trying to analyze and model the fragmentation. So the idea is there are 4 possible options in case that we have a rockfall. We may start with a single block in which nothing happened. The block falls, it rebounds, but there is no breakage. You may start with a single block, and this block may break. And then from the block, we obtain a volume distribution of the fragments, that we call rock block size distribution of the fragments. We may start with not with a single block, but a rock mass, which is defined by rock and discontinuities. So we start with what we call with an in situ block size distribution. We have not only one block, but a set of blocks, a collection of blocks that they fall together. And again, we may have simply a disaggregation of the mass, no breakage. So both distributions, the in situ block size distribution and the rock block size distribution coincide. Or we may have, which is more frequent, disaggregation and also breakage of the blocks, of the initial blocks. So we start with the in situ block size distribution and we finish with a rock block size distribution. We try to model this. So some of our PhD students, they work to develop models to reproduce this behavior. Okay, this is why it was proposed, a Rockfall fractal fragmentation model, because we, as I mentioned, fragments follow a fractal law. They follow a power law. So Roger Ruiz Carulla, he developed a model that was based by the work of Perfect, in which, starting from an initial block, we need first to define the largest fragment, and then from here we are computing one by one iteratively the rest of the fragment until the number of fragments fulfill the initial volume. We may do this, do the same, just instead of using the largest fragment, the dimension of the fragment, we may start with the initial volume, with defining a maximum fragment, the volume of the maximum fragment, and from there we may obtain the rest of the volume of the fragments. And there are some parameters of this equation. One is the fractal parameter, another is the largest fragment that we obtain. These two parameters are dependent, are a function of two other parameters, that is Q and B. B is the relationship within the initial block, let's say the father block, and the son block. If it has a length L, this block has half of length. So from this original block, we obtain here 8 smaller blocks. And this is what defines B parameter. And the Q parameter that affects or is what we consider by defining the maximum fragment is what we say the survival rate, which is 1 minus the probability of failure. That means which is the fraction of the block that is broken. So in case we break 1/8 of the original volume, in this case we break half of the original volume, but the fragments that are produced follow this ratio. Well, this model has been improved as considering that variant or invariant scale behavior, so that we may just read the details of this model in these 2 works that were published. And just to perform the model, we need to start with this original volume. How we obtain the in situ block size distribution? The in situ block size distribution may be obtained first defining which is the size of the unstable mass. In this case, at the beginning, we use the model. The model simply calibrate events. We observe which was the original mass, and we observe what are the fragments produced. And then we try to fit both the original mass with the fragment produced. So we need first to define which is the mobilized mass. For instance, we may obtain the size of Rockfall by subtracting the digital surface models before and after the event. Then in this mass that has been detached, we may just looking at the occur using these photogrammetric techniques, we may obtain the deep angle of the joints. We may identify with count compare or other type of software. We may identify the joints that are present in this outcrop, and then we may combine the joints identified using the real spacing and cut this original volume, with identified joints, in this case assuming that joints are fully persistent in the block, and we cut this volume, for instance, with Rhinoceros or other type of software. With this, we obtain the in situ block size distribution. And this is the in situ block size distribution, and applying the model, the Rockfall fractal fragmentation model, we obtain the final rock block size distribution. As we see, the size, the maximum size has been reduced. This is in cubic meters from several hundreds to a few tens of cubic meters. The maximum size has been reduced, but the number of blocks has been increased substantially. In this case, more than 2 orders of magnitude. Well, we tried to calibrate the model, visiting different rockfall events. So we did the inventory of several rockfall events in the Pyrenees area where we work, and these are the results. This is the in situ block size distribution in blue, and then in red, this is the rock block size distribution that has been observed in our inventories, and in green are the results of the Rockfall fractal fragmentation model. And as you can see, results match pretty well. So we were quite happy about this calibration. What happened, this is simply calibration. We just fit the observations with the model. The question is, we would like to be able to use this model for prediction, just to see what, if we know potential rockfall mass or rockfall volume, what can be the final rock block size distribution. And what we observe in these cases is that when we produce fragmentation, this is the area of the surface of this block. When it fragments, the area increases because we create new fragments, new faces. That means the area of the surface of these blocks increases substantially to give a total area. Here on the bottom on the left, there are some examples of the events we inventoried. This is the original area in blue, and in orange we have here the new area created. In this case, the new area created is only the 21% of the final area obtained. That means, okay, we have increased the area of the blocks, but not much. It's only 20% of the total area. But instead here, this is the original area. This is the Monasterio de Piedra. This is the area of the original in situ block size distribution. And this is the final area, which has increased at least 4 or 5 times the original area. That means this event was quite energetic because it break a lot the original mass, produced a lot of fragments, and increased substantially the area. And what we observe from our data is that this increase, that this is the total area over the initial area. That means the final area has been increased several times in some of the events, like here, this is correspond this point. This increase of area ratio has a kind of relationship with these parameters B and Q of the fractal fragmentation model. So in order to run the model, we need to know B and Q. And we see here that the B and Q are related to this ratio, or are related to the new area created. In fact, on the other side, we realized that in these events we inventoried, that there is a relationship between the potential energy and the new surface area created. This is not new. Other researchers have found that there is the amount of new area created by fragmentation has to do with the energy of the impact. Then here this relation is also observed. So we see here our events and how, depending on the potential energy, we create more or less a new area. So we have a relation between the potential energy and the new area created. And on the other hand, we have a relationship between the new area created and the P and Q parameters of the model. That means that, okay, we may proceed with this forward analysis, with this type of prediction analysis, is we know what is the size of the potential block, unstable block. We know the original volume, or we know the in situ process distribution. We know the initial area of these blocks. If we know as well which can be the height of the fall, we may estimate the potential energy of the first impact. As we have this potential energy and we have the original area, with this potential energy, we may obtain the new area surface generated, because we have this relationship that we observe. And with this new area generated, we may compute this ratio, new area over total area. And then from there, we may derive which are the parameters B and Q of the model that we need just to obtain the final rock block size distribution. Okay, so with this model, we try to simulate fragmentation, also beforehand, just knowing the size of the unstable block, and also which is the potential energy. Another model that was developed. This was developed by Gerard Matas. He prepared a Rockfall propagation model that is called Rock GIS. The idea is, okay, we start the simulation, the blocks fly through the air, they impact, then it asks, it stops, yes, then in case it stops, the simulation is ended. It does not stop, then the model asks whether it rolls, there is rolling or not. If it goes to rolling, then there is a module that, an algorithm that compute the rolling process. Otherwise, it is a rebound model then the block rebounds, and then the code asks whether there is breakage or not. In this case, the breakage is defined by an energy threshold. In case it breaks, then we start with a module of breakage criterion. Okay, the block breaks, then the mass has to be distributed among the different fragments, new fragments generated, and then we have to define the output trajectories that from our field test, we obtain this cone of this parabola, this cone of trajectories that is assigned to the fragment that has been produced, and then it continues the propagation, and again goes to this point, and then a new impact, and the same questions are put again. Okay, these are the results of this GIS code, in which we see here with a code of colors. The green means low velocity, yellow and red means higher velocity, that means higher kinetic energy. This model was just tested and calibrated in some field cases. This is one in the Pyrenees, in Vilanova de Banat, in which we here it is the slope before the event, and here we have after the event. We see that a young debris cover has been generated by the fall of this large rock mass, and also we may observe large scattered blocks on the slope. So it is what I mentioned, like a fragmented rockfall, because we have here a young debris cover, but also many scattered blocks. Okay, the calibration of the model was done, and also here we see the difference of computing the model with or without fragmentation. In the middle, the image in the middle corresponds to the observed deposit. This is the young debris cover. This is the large scattered blocks that has been observed and inventoried in the field. And this ROM corresponds to the center of mass of the deposit. If we perform the analysis without fragmentation, this is what we get. Circles are proportional to the size of the blocks. And what we see here is that without fragmentation, we produce larger fragments, larger than observed, bigger blocks. And also, we observe longer traveling distance than the observed. And this is a track, a small trail. And we will see here that more large scattered blocks pass across this track more than what we have observed. On the contrary, this is the image on the right. This is the modeled with GIS. We see the center of masses corresponds pretty well. We see the boundary of the young debris cover fits pretty well, and also that the larger scattered blocks more or less follow the same distribution. Maybe it's something that does not work so well is the size of the fragments, which is in reality are much bigger, or slightly bigger than the fragments that we obtain with the model. Here is another simulation with this GIS model. In case this, it was an event here of 50 cubic meters that was invented as well. And these are the simulation. In these 50 cubic meters are released 1,000 simulations, and we see which are the results. So we see here that this is the road. All the blocks, most of the blocks pass over the road, and with relative high energies. Here's the simulation for one single block of 50 cubic meters, and this is the simulation of the block of 50 cubic meters that fragments along the path, and this is the trajectories, and they match pretty well with the observation we obtained in our inventory. Okay, just to put an example of the capabilities of this model, let's see what are the effects of this fragmentation on the risk analysis. This is the risk equation that I think most of you will be familiar with. risk is a cumulative function. In fact, we try to compute the risk and hazard and risk for different volume, different size of events. So this is the risk due to the detachment of a cliff, of a rock mass, of a volume I, overexposed element J located at a distance x from the source. So the hazard is defined by the probability of occurrence, in this case, by the annual frequency of the events. Then we need to know which is the frequency of the events, of the rockfalls. Then if the rockfall occurs of this size, what is the probability of reaching a given location? So we need to know which can be the trajectories, and then to know which is the probability of reaching a given location. And then what is the exposure? That means the probability, the spatio-temporal probability of the exposed element to be in the trajectory of the rockfall at the moment that the rockfall occurs, the vulnerability, and the cost. Well, let's put a practical example of a quantitative risk analysis with these models of the Rockfall fractal fragmentation model and the Rock GIS. This is a case of 2017 that is a place in the middle of Spain and in Monasterio de Piedra. It's a natural site that it received more than 250,000 visitors per year. So it's quite crowded, this place in many occasions. And an event took place in February 2017, in which 800 cubic meters of rock fall on the trail that the visitors used to pass. Okay, here the analysis tried to demonstrate what are the effects of fragmentation and the potential of using these tools for the quantitative risk analysis. The area is a limestone cliff. In this case, failures occur in a variety of mechanisms. Sometimes what we see here, we see a crack, and we see that this rock mass, is laying on this small part, which is becoming more and more fractured by compression. Here we have some pieces of rock that they are broken and they act as an active wedge. So sometimes the failure is produced because this toe breaks, or sometimes because when you fill also with water, we produce an active wedge that makes all this column to topple. These are other examples on the right, in which we see the joints, which are daylighting at the outcrop. So they fulfill very well the kinematic analysis, the stability kinematic analysis. What happens is they do not fail, because even though they theoretically should fail, there is rock bridges that we cannot see, and it keeps it for a while as stable. This is what makes us suggest the possibility of analyzing as a risk, not specifically every single location trying to perform a deterministic analysis, but a probabilistic analysis using this quantitative risk approach. Okay, here, just for simplicity, just we're going to present the results of two analyses, the two alternative trails. Trail 1 runs below the cliff, but just below the cliff there is a gentle slope before reaching the trail, and trail 2 runs just immediately below the cliff, a vertical cliff, so all the blocks and fragments fall directly to the trail. Trail 1 as well has different rockfall fences just to protect partially the trail. This is the slope of trail 1. This is the trail 1 here. Here we have the cliff, the rockfall fence, a gentle slope, and this is trail 2. Here we see trail 2 and the steep cliff, the vertical cliff. Okay, in this case, we try to obtain what could be the probability of occurrence of the annual frequency of the events. So we just obtain data from different sources, from the blocks that were retained in the rockfall fences, historical cases, and so on, and some well-known, some that we identify in the on the slopes. And with this information, we prepare this magnitude frequency relation of the events, and we come out with the results. This is different volume classes, less than 0.005 cubic meters, and so on. And this is the frequency obtained with our inventory. So it's then we calibrate the RockGIS model with large events like that occur in 2017, and we try to, from the in situ block size distribution, to obtain the rock block size distribution, the final rock block size distribution, and also the calibration of some work that were done before, some scaling works in which blocks fall in the slopes, in the bottom, and then everything was just back analyzed with the program. And here there are some outputs of the RockGIS code. Here is the results for 5 cubic meter block with no fragmentation. We see these red colors, yellow colors, that means high velocities, high energies. And this is when we experience fragmentation. This is the trajectories. You are much shorter. And also the green color means less velocity, less kinetic energy. And also for the exposure, we use the Nicolette expression, in which it is considered the flow of the visitors, the width of the rockfall, the width of the people, and also the velocity of the people just that moving along the path below the cliff. And as the rockfall increases the affected area due to the divergence of the trajectories, we also just corrected this width of the rockfall, because if the rockfall was the whole mass was the rockfall was simply a huge front, then the width will be exactly of the front. But when we have scattered blocks, the rockfall does not occupy the whole width. So we just correct the width depending on the number of blocks that reach this given section. The details you may find in the paper we publish on this. These are the results. And the results, what the results show is a contrasting effect of fragmentation. But we see this is a steeper slope in which the fragments just fall almost directly onto the trail. And we see that when we consider unfragmented rockfalls, and we consider that a rockfall fragment, the risk increases, doubles. Why double? Because well, I'm going to explain in a minute. On the contrary, when we consider the gentler slope, what we observe is we deal with unfragmented rockfalls. We have a high risk. This is the annual probability of losing the life here. It's quite high. But with fragmentation, the risk is reduced 2 orders of magnitude, which is quite a lot. Why this happen? We have an increase of risk in the steeper slope because as most of the blocks reach the bottom, reach the trail, so there is no, most of the block reach the trail, there is no effect of losing the energy along the path. And what happens is that the exposure increases substantially because this divergence of the trajectories, exposure has increased substantially, and it's what we see here. Exposure from a small block, this is zero, the probability of spatio-temporal probability of being someone in the trail at the moment of the rockfall. Here is 0.01, and here is 1 order of magnitude bigger. Sorry, this is 4 times more, and here is almost 1 order of magnitude bigger. So we see that by increasing the divergence of the trajectories, we increase the probability of impact on the exposed persons. And this is the reason why we increase the risk in the steeper slope. But on the contrary, Sorry. On the contrary, what we see here in the gentle slope is that the risk is reduced substantially. And why is this reduced? In one side is that most of the small fragments, they are not able to reach the trail. Why? Because small fragments, they mobilize less energy, so they are not able to reach the trail. The large fragments, they do. So the risk, the reduction of the risk is mostly due to the fact that the small fragments, when we have fragmentation, small fragments are not able to reach the trail. And this is the reason. Another interesting issue is to know whether the risk, most of the risk is due to large events or small events. And here what we see is the highest risk values are associated to small and mid-sized events. Here we see for different ranges of volumes, that risk, this is the annual risk, this is the 2.3 10 to minus 2 annual probability of losing the life, is due basically to these small size events in case that we have no fragmentation. On the contrary, when we deal with large events that they are less frequent, they may reach easily the trail, but because they are not so frequent than the small events, risk due to these events is much smaller, several orders of magnitudes smaller than frequent small size events. This is something that's interesting because sometimes there is a debate on whether risk is bigger due to the large events, large uncommon events, or frequent small events. And finally, just to see the efficiency of the fences, this is the results of trail 1 where we have the fences. This is the initial situation of the slope on top, and this at the bottom there is the situation with the fences. When we have unfragmented rockfalls, what we observe that the risk is substantially reduced due to the fences. Why? Because fences stop most of the small blocks. We see here the reach probability of the rockfall reaching the trail that has been reduced 1 order of magnitude compared when we have no fences. Here is without fences, and here is with fences. This is the reason that risk is reduced. On the contrary, when for fragmented rockfalls, as fragmentation makes that small size events do not reach the trail, then this effect of fences is not significant here. There is a slight reduction, but very small reduction because large events have enough energy to break the fences. Well, these are only examples, and then I'm going to the end because I'm over the suggested time. We conclude that analysis of fragmentation of rockfall is necessary because it has a lot of influence on the results of risk and also for risk management. One of the main effects is the rockfall fragmentation reduces the rockfall propagation if the slope is gentle and long enough just to let the small fragments stop. But this effect vanishes with the rock size. And also an important effect of fragmentation is that increases exposure substantially because the affected area is much bigger. So if you are considering moving elements like cars or people, then the area affected is increased. So we have this contrasting effect that in one side we reduce risk due to the small fragment, they don't go so far away, and on the contrary, the divergence of the trajectories produce bigger exposure and then increase risk. Okay, this is a list of reference that of my presentation that you may check, but I suggest going to these web pages in which we have all the information of our research results and also some demos of our codes that we developed in the research projects. And I would like to thank my colleagues. This is in the test we performed, and thank you very much for your attention. I'm open to your questions.
Thank you very much, Professor Corominas. It was, I think, a really interesting presentation, and there are already some questions, so I think it's better to start. If you would like, you can open the chat session. It's in the bottom on the banner next to the share screen button.
Sorry, I think I missed. I did something that I missed. The I just went out of the Zoom.
Okay. Just.
I try to get in again.
Can you hear us?
I can hear you.
Ah, okay. Probably it's if you go to the page that you're sharing, and probably by stop sharing.
Yeah, but I missed the screen.
Okay.
No.
Now it's okay.
Okay.
So in the bottom there is a chat session. If you would like to open it to be better for you. So I will start with the first question. It's saying, for the PowerPoint slide showing rock GIS, were the sizes of the fragmented materials observed measured using photogrammetry, or was it measured directly by field personnel? The photo shows that some of the material is very difficult to read, so I'm curious about the accuracy of the measurements.
Showing rock GIS where the size of fragmented material observed. Maybe I went too fast. The inventories, Rockfall inventories, we all has been measured in, let's say, twofold. On one side, we measure by hand. So we spend many days measuring fragments, sometimes just preparing sampling plots where we spend many days at the beginning measuring by hand. Then what we have done is measuring by hand and measuring using photogrammetric techniques, using orthophotos, and measuring the area of the projected area of the fragments. And then because these fragments were measured by hand, we established a relationship between the area and the volume. And also we have checked doing this automatically and to see what is the area obtained automatically without measuring. So it's, we have done all the type procedures just to check that our measurements make sense.
So next question is, in an area with frequent rockfall, previous faults usually creates talus. How do we consider the effect of rockfalls on loose talus rather than a solid surface? Well,
this is an all question in the meaning that we just for rock GIS we have to define two parameters. One is the coefficient of restitution, because solid ground usually provides coefficient of restitution much bigger than the soft ground, and also on the rugosity, because if this talus is formed by large blocks, small blocks just traveling over the talus may be interrupted, may be intercepted by the bigger blocks. So that these two effects may condition the results of the model, and both effects have to be considered in the modeling.
Next question is, did you consider rock strength in your analysis for fragmentation? For example, sandstone has a higher chance of being fragmented when compared to volcanic or metamorphic rocks.
Surely should have this influence. We are convinced of this. What happened is because we wanted to understand other features of fragmentation, the tests that we performed were made in the same lithology, mostly limestone, in which we measure the neaxial compressive strength and also the tensile strength. What happened is so far we were not able to identify a relationship between the strength and the pattern of fragmentation. The strength, of course, make that block may break or not, but it's not so clear because it's not a direct relationship. So we need to perform more analysis with more type of rock, because of course we are convinced that there must be an influence of the strength of the rock.
Next question is, have you examined the relation between the volume distribution fragmentation parameter and the in situ rock joint spacing distribution? If yes, is there any correlation that allows to estimate this parameter?
Well, I would say we did not find a relation between both. What happened, we need both just for our analysis. So we need an in situ block size distribution because when we observe the fragments after the rockfall event, this fragment may derive from one single block or from a rock mass. So to run our model, we need to analyze the source, from the source extract the discontinuities that we observed then, and then the volume, the missing volume, is cut with these discontinuities to define the in situ block size distribution. But there is no direct relation between the in situ block size distribution and the rock block size distribution, because it depends on the degree of fragmentation. This has to do with other factors, like the potential energy, like the stiffness of the ground, and there are other factors that affect the final rock block fragment distribution. So we don't expect that this relation occurs.
So I think we have time for one or two questions. For larger blocks, it is taken into account the influence of block shape and slenderness in the fragmentation model?
Not in the fragmentation model. Of course, we know that there is an effect of the shape of the impact, whether it impacts on a vertex or whether it impacts on a face. We are trying to analyze this in our tests, the queries we perform, but they has not been incorporated yet in the Rockfall fractal fragmentation model.
Let's have one more question. It's from dear Professor Corominas, very interesting presentation. Thank you very much. Just a quick question regarding your Rockfall fragmentation model. Do I see it correctly that the fragmentation model only considers orthogonal fracture patterns, or is it also possible to consider more oblique fracture orientations, irregular discontinuities without arrangement into distinct sets?
I don't know whether I understand properly the question. The fragmentation model is not georeferences, that it does not consider the joint pattern inside the block. The fragmentation model is conceptual. It means which is the part, how much block breaks. So we estimate which is it breaks 80%, it breaks 70%, it breaks 60% to define the largest block, and then the following blocks. But we don't. This fragmentation is not obtained by considering the joints inside the block.
So I think it's time. I would like to thank you, Professor Corominas, for your presentation. I think it's time to move on to our next presenter.
Thank you.
Our next presenter is Dr. Anika Braun. She will present about the topic on machine learning for landslide susceptibility mapping with a case study of rockfall onset probability modeling in Saxony, Germany. Dr. Anika Braun is a lecturer at the Department of Engineering Geology at the Institute of Applied Geoscience at the Universität Berlin in Germany. She obtained her bachelor degree and master degree in georesources management in 2008 and 2010, as well as her PhD degree in engineering geology in 2015 at Aachen, Germany. From 2015 to 2018, she completed a postdoc at the Institute of Geology and Geophysics at the Chinese Academy of Science in Beijing, China. In her research, Anika focused on different types of mass movements using a wide range of field modeling and remote sensing techniques. She has studied mass movements in several countries, including Germany, Spain, Kyrgyzstan, China, Honduras, Cameroon, and Colombia. Anika is the secretary of the German Engineering Geology section and member of the early career chapter of the German Geotechnical Society. She is also our country representative for Germany as the e-YEG group. Now, I would like to welcome Dr. Anika. I would like to ask you to unmute yourself and turn off your camera. The space is yours. And thank you very much for being here today.
Okay, Stratis, thank you so much for your kind introduction. I hope you can see my screen and you can hear me well.
Yes, yes.
Great, thank you. Thank you so much. Okay, yeah, I really want to thank the young engineering geologists for giving me this opportunity to present at this webinar. And yeah, I think it's not so easy to present after a legend like Professor Corominas, but I will try my best. Yeah, so as Stratis already said, today I want to talk about machine learning for landslide susceptibility mapping, because this is one of the main topics I'm doing my work on. However, because the topic of this webinar was supposed to be about rockfall hazard, I brought for you a case study where we actually implemented machine learning methods for rockfall susceptibility modeling in a study area in Eastern Germany. And then because the title also mentioned some future considerations, I also will try to pick up on that in the end of my presentation. Okay, so yeah, let's get started, and maybe first talk a little bit about what machine learning is. So in the 1950s, a new field of computer science came up, which is called artificial intelligence. And artificial intelligence is actually more of an umbrella term for all different fields of computer science where we try to make machines do intelligent things. And so one of the first examples are, for example, chess computers. Maybe you remember the day when the IBM computer beat the world champion in chess in a tourney. So this is an example of artificial intelligence. Then later in the 1980s, the field of machine learning came up as a subset of AI. And this is a field where we actually use algorithms that can learn from data. And based on this data, they can make predictions or take decisions. So this is what machine learning is about. And maybe you've heard of some of those algorithms like artificial neural networks, decision trees, or logistic regression, for example. But in the beginning, this was not so very exciting. But after some time, when the computational power increased and also the amount of data that was available, people could actually start to do really interesting stuff with those machine learning algorithms. And this is also when another subset of machine learning came up, which is called deep learning. And deep learning is basically just a special kind of artificial neural networks that have a lot of layers. And by this, they can solve really complicated problems. And so I think those are some of the buzzwords that you hear a lot nowadays, because after this revolution of computational power and data availability, those techniques really started to be able to solve really big problems. I think nowadays probably all of you are using machine learning in your everyday life. For example, using face recognition on your phone, or using speech recognition to talk to Google or Alexa or so. And we also have a lot of tasks in engineering geology that we can solve with machine learning. One example is the automatic detection of objects or features for example, in optical images or in digital elevation models. So we can use this, for example, for automatic landslide mapping. So Stratis has done a whole webinar on this topic. So this is a really interesting new topic. We can also use machine learning for doing time series analysis. And of course, we can use it to do landslide susceptibility mapping, which I will be talking about today. Okay, so let's just also define what is landslide susceptibility. This is basically the spatial probability of landslide occurrence, or the spatial part of landslide hazard. We could also define it as areas. So areas with a high landslide susceptibility are prone to slope failure, or that a landslide may travel onto or retrogress into them. And this distinction is actually really important when talking about rockfalls, because rockfalls are really mobile mass movements. So they usually the failure occurs usually in a steep rock cliff or something like that. And then the rockfall can travel really far. So actually the area that it may travel onto is pretty large. So it's really important to differentiate between those two things. And what we do with landslide susceptibility is we try to map it. And then we can basically subdivide the terrain into zones of similar likelihood of landslide occurrence, as you can see in this example here. And we can use those kinds of maps, for example, in urban planning. We can use this as a basis for a quantitative risk assessment. So those are some of the cases where we need this. Let me very briefly go over the methods we have for landslide susceptibility assessment. The most important groups are the knowledge-driven methods that are qualitative methods, and then we have physically based methods and data-driven methods that both allow quantitative analysis of landslide susceptibility. And we are focusing today on the data-driven methods. And the ironic thing is maybe a little bit that data-driven methods actually have the least requirements in data, or less requirements than, for example, physically based methods that need a lot of data that has been gathered through field testing or lab testing. So in data-driven methods, we can use remotely sensed data, and this is usually more easily available now more than ever. So how does it work? What we try to do in data-driven landslide susceptibility assessment is the quantification of the relationship between the occurrence of landslides and predisposing factors that we believe to be related to the occurrence of landslides. And the fundamental principle behind this is that we assume that situations or conditions that have led to slope failures in the past, that we can kind of gather by looking at past landslides, that those conditions may also lead to slope failure in the future. And so the main goals we follow by this kind of modeling is that we want to try to identify areas where landslides are likely to occur in the future. But we could also, what also would be great would be if we can come up with a model that we can use for a new area where we, for example, don't know where landslides have occurred before, and we can just put in the information on the predisposing factors to come up with an estimate of landslide susceptibility. So let's take a look what kind of methods we have among those data-driven methods. So we have, on the one hand, we have bivariate statistical methods. Those methods are quite simple. They are really easy to put into practice, and they are also really easy to interpret. So those methods are really a good starting point to get a first idea of how the landslide susceptibility looks in your study area. But for getting a deeper understanding, you actually need methods that can account for a combination of different factors at the same time, and that can also analyze large data sets and really complex situations. And this is where the machine learning methods come into play. So here in this overview, they are called multivariate statistics and artificial neural networks, but those are basically all machine learning methods. But why machine learning? So I already said with those methods, we can analyze much bigger and more complex data sets. And actually, in the past years, there has been a massive increase of availability of such data. So, for example, in the past 5 years, there were at least 4 global digital elevation models that have been released to the public for free. And of course, there are also a lot of optical and radar satellites that are out there now and whose data we can use for free. Many country or local authorities are also putting their spatial data online for everyone to use. In the EU, we have, for example, the INSPIRE framework. At the same time, we also have an increase of availability of software tools that we can use for machine learning. The computational power, of course, also increased, and also the know-how. So today, everybody can learn machine learning by watching some YouTube videos, or at least start to learn it. And this is also the reason why in the past years, the number of publications on susceptibility studies using machine learning really exploded. So you can see here a figure that I took from the really great review paper from Mergadi et al. They did a review of basically all the papers that used machine learning for landslide susceptibility mapping in the past years. And you can see here how for different algorithms over the years, the number of publications really increased. So yeah, this is crazy how this publication activity increased with those methods. So yeah, the basic idea is really that we can extract more useful information from such complex and big data sets that can help us understand better the spatial patterns of landslide occurrence. Here I have a slide where I just want to explain a bit more into detail what kind of data I'm actually talking about. So of course, we need to know where previous landslides have occurred. So for this, we usually use landslide inventories. Nowadays, they are also easy to map because we have all this satellite data available that we can use for mapping landslides. But we also need some information on the parameters with a possible relationship to landslide occurrence, so-called predictors. And here you can see an overview from another review paper from Reichenbach et al., who reviewed 565 publications on landslide susceptibility, and they kind of tried to make an overview of the most commonly used parameters in the study. So you can see there are some morphological parameters, geological, land use. There are also hydrological parameters that are popular to use in such studies and that are believed to be related to the occurrence of landslides. So this may be as a brief introduction into what the whole concept is of landslide susceptibility and why we see a lot of potential in using machine learning for this task. And now I want to take you a little bit through the process or the workflow of applying machine learning for landslide susceptibility mapping. And so the main thing is that we kind of have to create a mathematical model of the real world that we can then analyze with those machine learning algorithms. So here, I prepared an overview of the whole workflow, and I would just go through this step by step. So it all starts by actually defining the question. So what you actually want to model. And you should be quite clear about this in the beginning. And you should also consider what kind of data you actually have available and whether the question you are asking could be solved using the data you have. So, for example, maybe you want to just detect landslides in a data set, or you want to rather create like a susceptibility maps with different zones of landslide susceptibility. And then maybe you want to analyze a certain type of landslide, and then you just have to figure out if you can do that with your data. And so the next 3 steps in this workflow, they are all related to the data and the preparation and collection of data. And this is really one of the most important parts of this machine learning workflow, which is also, as you can see here in this bar, also most of the effort of this work. So we start at the real world and we collect some data about it. Usually we do this in a GIS. So maybe we have some data from field mapping, we have some remote sensing data, and we put this all in a GIS, and we process the data further. So for example, maybe we have a digital elevation model and we can derive a lot of morphological information from this, for example. And after we have finished collecting all the data in the GIS, we basically sample this data into a table. So we usually do this by defining some kind of spatial discretization we can use to make every sampling unit that we use line in the data table that we get. So usually this sampling unit are raster cells, but you can also use, for example, slope units. And then each of those raster cells or slope units becomes a line in this table. And then we can go into the next step, the data preparation and data exploration as well. So we go through the data and then we try to get an idea of the data first. And so, for example, as I said, what we are doing is we are creating a mathematical model of the real world. And this is actually where we as geologists or engineering geologists have to put our mind to, because we need to find meaningful ways how we could mathematically represent the parameters that we mapped in the real world. So one example is the slope aspect. As you know, the slope aspect can have values between 0 and 360 degrees. The thing is that 0 and 360 both means north. But mathematically, it's very, very far away from each other. So we need to find a way to mathematically present this aspect. So it's actually also mathematically kind of reflecting the nature of this variable aspect. So one solution would, for example, taking the cosine from this aspect variable. So this is just an example. This is really important that during the preparation of the data, that we really have some domain knowledge that we can put into this to be really smart about how we prepare the data. Then during the data exploration, we can also try to figure out if we maybe have data that has a low quality that we can kick out already, or whether, for example, we have some parameters that strongly correlate with each other, then we can maybe decide to kick one of them out as well. So this is just the first exploration of the space of our data. And then, of course, one thing we also have to do is we have to scale the data or normalize the data to bring it all on the same scale. So there's no mathematical over representation of a variable, for example, that has really large values before this normalization. Those are just some things you do during this data preparation, so you can maybe start to understand why this is 75% of the effort of this whole machine learning workflow. So after we have our data neatly prepared, we can finally start with the modeling, which is taking up probably only 15% of the effort. And so how machine learning modeling actually works. So in our case, we are working with supervised learning. So this means that the algorithms, while they learn from the data, they know what the outcomes is. So we want to predict landslides. So during the training phase, the algorithm knows for each record in our data set whether this is a landslide or not. So then we start, we first randomly split our data set into a training and a test data set, and then we run this training data set through the algorithm, and the algorithm is learning from this data what a landslide looks like in our data set. After the training is finished, we take the resulting model and then we run the other part of the data, the test data, through this model, and then we see what the outcomes is, and then we can compare it to the actual observations. and then we can figure out whether this algorithm performed well or not. And this is basically the main goal of this modeling process. We want the algorithms to develop a model that can be generalized to new data. So this is just the main goal or the main problem, to create models with the ability to generalize. And yeah, so we evaluate this, of course, and then we have another tool that is really commonly used for the evaluation of such models. It's called the receiver operator characteristics curve. So this is actually just some graphical plot that can help us figure out whether the result of our model is useful to classify our data set into landslides and non-landslides. So it should be a good measure to just split the data into landslides and non-landslides with as little errors as possible. And then another part is that we also, of course, need to look at the result in the spatial context. So we would usually map the result. So basically the outcomes of this modeling is a probability whether a data record would be a landslide or not. So it's a probability from 0 to 1. And so 1 means landslide. And usually, so we use this probability to plot it in a map. And then we could use this to define different zones of landslide susceptibility in the map. And this is the thing that many models that seem to perform really well, looking at for example, the receiver operator characteristics curve, or looking at how many landslides were correctly detected by the model. But then the map looks really not so useful if you think whether you would use this actually in planning or for taking decisions. So yeah, you really need to also consider the spatial performance of such a model. Yeah, and then if you're not happy with this, you can go back to any of the steps along this process to try to improve the model. Maybe you even have to go back to the start and define another question or change your question. So this is basically the whole process, and I prepared a lot of slides to go into more detail about some of those steps, but I think I'm talking way too much, so I think I will skip some slides. So we still have enough time for looking at a case study of Rockfalls, which is the topic of this webinar. So, okay, this slide is important. This is a really important question. How much data do we actually need for this kind of machine learning? This is actually a question where I have no answer to it, and there's basically no unified recommendation as to how much data is enough for machine learning. So there's no law that says, okay, you cannot do machine learning if you have below 1,000 data points or something. It's just, the thing is just that some algorithms, the more data you present to the algorithms during the training, the better they can learn. So it's just probably they will not reach their full potential if you don't have enough data. So yeah, this is kind of the vertical aspect of data quantity. So the number of data points, which of course depends completely on the size of your study area, on the resolution, also how much computational power you have to process so much data. And then we can also look at this question horizontally. So this means like, how many variables do we need? And here again, the Reichenbach review comes quite handy. So in those 565 articles, between 2 and 22 variables were used. In such kinds of studies, 9 on average, although those are also, I think, a lot of studies on more simple bivariate statistical methods, which use very often, between 5 and 7 variables or so on. In machine learning, you actually need more. So we have found in our work that in general, the more variables you use in a data set, the better. But this, of course, also depends a bit on the algorithm. So, for example, if you're using artificial neural networks, for us, it's always the more variables you have in the data set, the more landslides they can detect in the end. And also the more specific the maps get. So, yeah, that's at least something from our experience. But I think this is something we really need to talk about more in the community, like how much data do we actually need to create meaningful outputs. Yeah, another thing I just quickly want to touch is the topic of mapping units. So yeah, the most simple and also most popular mapping unit is just the grid cell, which is probably understandable. But there's also another type of mapping units called slope units. So slope units are like hydrological or geomorphological terrain units that are supposed to represent single slopes. And I really like this concept because I think this representation of a whole slope is really more, it's really more reflecting the whole conditions that lead to slope failure. And I'm really sure that this is also a better concept for communicating landslide susceptibility or landslide hazard. And also, for example, if you have landslide inventories with a high uncertainty, or for example, you only have points of landslides, then this is also a good way to kind of spatially discretize where your landslides are. But there are also some problems. So, for example, usually you sample the data per slope unit. This means that every slope unit is one data point in your data set. And if your study area is not so big, you might end up having not enough data points to do meaningful machine learning. So this is another thing to consider. But I think I have to move on to the next slide. So I talked already a lot about those things, so I will skip those slides. There's just one point I really want to also highlight. So one problem we often have in machine learning with landslide data sets is that landslides are often really largely underrepresented, which is, of course, making sense. But it's not so easy for the machine learning algorithms to learn what landslide cases actually look like. And in machine learning, it's usually recommended to use at least 30 to 70% ratios. So we would need a data set with 30% landslide cells or landslide records. So there are some tricks we can use to improve this balance in our data set. So the first one would be balancing by just duplicating the landslide records we have in the data set. And another solution would be undersampling. So this means we take all the landslide data, but we take only a part of the non-landslide data. And by this, we can increase the ratio of landslides. And another thing is that often we have really large study areas where we can actually not analyze all data points because, not everybody has a supercomputer. So it's necessary to sample anyway. So this is just an example from our Rockfall study that started with 19 million data points. So this was really too much even for our workstation to process so many data points. Okay, just small note also on the way we evaluate such models. So as I already said, the outcomes would be a probability between 0 and 1 of being a landslide. And strictly, we are doing a binary prediction. So we just want to know landslide, yes or no. And so we usually use a cutoff value, for example, 0.5 to say like everything with a probability above 0.5 is a landslide. And pretty sure all of you know this confusion matrix. And also after this pandemic, or still in the middle of this pandemic, I'm sure that most of you also have heard the terms sensitivity and specificity that we can also use for this kind of binary landslide prediction, so the true positive rate and the true negative rate. And those are some like skill scores you can use to evaluate the performance of your model. And yeah, I plan to explain those ROC curves more in detail, but I will skip this too now. And yeah, I just wanted to pick up one last thing concerning the spatial performance of such models. So here you see an example from a study that we did in Central Asia, in the Tian Shan. So you can see on the left the model of an artificial neural network on a full data set. And here you can see some spatial artifacts in this zonation map. And so just by changing the input data set, using only continuous variables and kicking out nominal variables such as lithology, for example, we were able to get a completely artifact-free map. So yeah, this is just showing also the impact that the input data can actually have on the modeling results. Yes, so let me come to the case study now. So I will finally start talking about rockfalls. So yeah, we did this case study related to a project that's called Mass Movements in Germany. This was a project by the Federal Institute for Geosciences and Natural Resources in cooperation with some of the state geological surveys we have in Germany. And so the whole goal of this project was to explore data that is available all over Germany, and to also explore different methods of susceptibility mapping for mass movements, how they work with those with this data. And yeah, in some case studies, they wanted to explore the potential of this data and of different methods, and if they could be useful to use, for example, on the country scale, or yeah, use this for the whole country. And so we were invited to participate in one of those case studies, which was here in the state of Saxony. This area is called Elbtalgraben, and you probably know the city of Dresden, which is located within the study area. And so our challenge was to use this database from this project that is available, that is covering all Germany basically, to use this data to analyze rockfall susceptibility. And this was done, by the way, by a master's student of our group, Felix Schumann, who did this work. So yeah, let's take a closer look at the study area. So here you can see that in the east of this of the study area, we are in a mountainous area, and this area is called Sandstone Mountains. This is actually a really also popular area for tourism. They also call it the Switzerland of Saxony. So in this area, we have those sandstones that form a lot of like steep outcrops and cliffs. And those sandstones, they produce a lot of rockfalls. And yeah, as you can see, the rockfalls we had in the inventory that the State Geological Survey shared with us, most of them were here in this area of the Sandstone Mountains. And yeah, in the western part of the study area, there were no rockfalls. But we decided that we wanted to cover the whole area because it's also important for the machine learning algorithms to be able to learn how to predict no rockfall area, or how to detect areas that have no potential for rockfalls. So yeah, this was kind of the challenge we got into. And then we defined our question, and we decided that based on the data we got, we want to try to model the rockfall onset probability. So this means this is just like the susceptibility the part of susceptibility where we consider the failure of the slope. So where are the cliffs where the rockfalls come from? And yeah, you might think now, okay, I can do this myself. Just tell me where the slope angle is steeper than, I don't know, 45 degrees, and this is where our rockfalls are. But of course, there's a little bit more to that. So, I mean, of course, obviously the lithology plays a role. But so the idea was that there's maybe even more to that. And we were hoping that we could find this out by using artificial neural networks with this data set. So yeah, the first problem we came across when starting with this challenge was how can we actually represent the rockfall sources spatially in the training so the neural networks get a good idea of what the rockfalls look like. So the problem was that we only had 356 points where rockfalls have occurred in the past. And also those locations were not like super certain. So there was a little degree of uncertainty about how those points were actually mapped. And so we came up with 3 different approaches how we could spatially discretize those areas that were identified as susceptible to rockfalls. And so we used a very simple method by just drawing a circular buffer of 25 meters around the rockfall points that we got. And we had a 10-meter digital elevation model. So this was kind of the resolution of the study. And so a buffer of 25 meters would catch like 32 raster cells that would represent this rockfall. And then Felix tried different methods that, yeah, he basically tried to create like really small slope units that could also represent this area of the cliff where the rockfall occurred. As you can see, it didn't work so well to map those really small slope units, but we took this anyway to see what the neural networks would make of this. And as you can see here in this table, we ended up with 6,000 to 10,000 or almost 11,000 grid cells representing rockfalls, opposed to 356 points that we had. But still, the percentage of the whole area was, of course, really low because we had this really large area where in the West not a single rockfall occurred. So yeah, this is quite clear. Okay, this is just, you don't have to look at all of this in detail. This is just an overview of the 22 variables that Felix derived from the database that we got from the BGR. And yeah, so there were some morphological parameters, some geological ones, some land cover ones, and then, yeah, those 3 approaches for spatially discretizing the rockfall source areas. And then Felix applied this undersampling technique to get a better representation of the rockfall cases of 30% rockfalls versus 70% no rockfalls. And yeah, here you can already see some of the results. So the first thing that we learned was that it didn't matter so much how we spatially discretized the rockfalls. So the results were quite similar. And then we kind of decided that the buffer method was the easiest one. So this one won, yeah, for the ease of use. Yeah, Felix also did some tricks to improve the performance of the neural networks. This is a technique called bagging, where the algorithm automatically splits the data set into several subsets, and it creates separate models for each subset, and then the different models will take like a voting decision about the result. So this actually helped also improve the performance even further. And now if we look at those like performance indicators for this model using the bagging technique and all 22 variables that were in the data set, you can see that we had really good like true positive rates of over 90%. And while the specificity, like the true negative rates, looked also quite good. But then again, so this would be, for example, 93% of the non-rockfalls were correctly identified, but this also means that almost 7% of the study area was actually recognized as a rockfall, like a false alarm, but it wasn't. And this is actually, quite much. And if you look a bit into more detail at this map, this is in the middle of the rockfall area where the rockfalls actually occur. So you can see, of course, the rockfalls were all captured by the high susceptibility zones, but also there's a lot of like high susceptibility zones. So I think this could be useful if you are more on the like regional level. So you can identify, okay, this whole area is really susceptible to rockfalls. But I think for planning on a more local scale, this map is not specific enough. You can also see some artifacts. So, for example, here in the city of Dresden, the model also captured highway ramps as rockfall cliffs. And also here in the west, in an area that had no rockfalls, of course, there were also some zones of elevated susceptibility. So, those were just some unwanted effects on the spatial, if we look at the spatial performance of this model. Here you can just see a comparison of the parameter importance. So this is for the standard model without this bagging technique. You can see that the morphological parameters made up more than 50% of the parameter importance, while, for example, geological factors were quite unimportant. But then after using this bagging method, you can see that it's much more balanced, and actually the geological parameters become much more important for generating this model, and the morphological parameters lose some of their importance. So this was also a really interesting finding from this work. And then Felix also went ahead and tried out different combinations of parameters by starting with a very basic model where he only used the slope angle as input parameter. And then he successively started adding more parameters. So he started first with only morphological parameters. He also tried to create some models just using geological parameters, which didn't turn out well, by the way. And then he tried some combinations with different parameters from different areas like morphology, geology, and so on. And so, the good news is that actually the models became more specific the more parameters he added. While, for example, the model with only considering the slope angle, of course, in all those areas in the West, a lot of like steep slopes were identified as rockfall cliffs who just were not rockfall cliffs because of maybe a different type of lithology or so on. And so this is also one of the results from this work. And this I want to skip this and just come to the conclusions of this study. So the numbers, if you look at the skill scores and also at the success rate curves that Felix looked at, the models look like they perform really well. But if you look at the maps, they kind of seemed a little bit too unspecific to be really useful on a local scale, in our opinion. But the good news is the models became more specific when we added more parameters to them. And it also turned out that the buffer was a simple and efficient way to spatially represent those rockfall locations. This is actually an interesting outcome because for us, this was also the first time to model rockfall susceptibility with this kind of methodology. And so this was interesting to learn. So the conclusions in the BGR report were that the results were satisfactory, but really not worth the effort compared to more simple methods that yield comparable results. yeah, I can understand that also, because rockfall susceptibility is maybe not the most complex type of landslide to model. But what I also want to say is that I really like this cooperation with the stakeholders who are actually supposed to use such models. And I really think that the people doing machine learning for landslide susceptibility modeling, they really need to talk more to people who could use this, and also learn about what they need, what their needs are for this kind of modeling or mapping. And so, yeah, maybe we will get more use cases of such modeling. So, yeah, if you speak German, you can also download the final report of the project, where you can also find some more information on our study. But yeah, it's in German, so maybe some of you can read it. So yeah, but this actually also brings me to some points I want to pick up for future considerations. So yeah, as I think, as I was able to show in the beginning, there's really a large number of papers on using machine learning for this field. But I think, yeah, it doesn't really correlate with the number of practical implementations of such models. At least I don't know of any. So this is something I would really like to start a discussion in the community about. Maybe you know of any kind of implementation of machine learning models for landslide hazard mapping. I would really be interested to learn more about this. So I think all those publications show that the algorithms work, but it seems a little bit like an academic exercise so far. And so yeah, I'm wondering, yeah, whether we could kind of elevate this on a level where it can be actually useful on an operational level, where actually stakeholders could use this kind of techniques. And so I've been thinking also a lot about this data part, because in our studies, it really showed that if you yeah, how great the impact of the selection of input data can be for the result, and also the quality of the input data, of course, is super important, especially if you start studying like really large areas. And maybe we can improve the reliability of such kind of modeling by harmonizing the data standards and also the machine learning process. And so yeah, there was this interesting project I came across last year. There's so I already mentioned this European Inspire framework, which is basically an infrastructure framework for spatial information in the EU. And it's also kind of making it mandatory for member states to release data according to this standard to the public. And so there was the startup that participated in a hackathon related to this Inspire data. And they came up with a use case where they kind of extended this Inspire standard for geohazard types. And then they used this data to come up with this susceptibility modeling for different types of landslides. And yeah, I think something like this is really interesting and something we should maybe start doing more. The same as the collaboration we did with the BGR. So this was really valuable for us. And I think really that we machine learning people need to start talking more to the people who could use this. So, oh yeah, by the way, these people, they also published a paper on this, so you can take a look at what they did if you're interested. Yeah, another thing is, of course, that we can still go bigger. There are so far still not so many studies who work on really large areas. I know that there are, of course, also some groups who are working on global landslide susceptibility, but there's also like a lot of space in between global and regional. So there are not so many studies on that. So we have tried this in 2 areas in Central Asia and also in Armenia. And another thing is how can we make such models actually transferable to new areas? And for making this possible, we also have, again, to go back to harmonizing the input data, because we can, of course, only transfer models to areas where we have the same input data that we can use for the modeling. And I think I'm really running out of time. I just had one last thing that I wanted to show, but then Professor Corominas kind of did this before me, because I just came across this case study where machine learning or deep learning was used for automatic detection of rocks in drone-based aerial images. And you can see here an example where this Raymond Arrowsmith, he's the person behind Open Topography. He mapped some rocks along a fault scarp using a drone. And then, he used this deep learning algorithm to automatically detect the rockfalls. And then he could use the high-resolution dam data from the drone to estimate the volume, the roundness, and so on. And then, of course, you can do some size-frequency relationships for rockfalls, for example. But the interesting part is that his group is currently developing a tool called Deep GIS. So this is supposed to be a GIS interface that people like us who are not so into programming or deep learning can use to do the deep learning from a GIS interface. And I think this is really also useful for engineering geology. So you can check out this website. He said the tool is supposed to be released soon. And so Professor Corominas also had some fieldwork pictures from his PhD. So here I have some fieldwork pictures from my bachelor thesis back in 2008, where I was also walking around for 1 week mapping rockfall deposits. So this work would also nowadays be much faster using a drone. But then again, with this amazing view from the study area, I also don't regret that I was able to do this work in the field. So this is my last slide. And I just want to thank some people like my supervisor, Thomas Fernandez-Steger, who was one of the first geeks in engineering geology who started working with machine learning, and also some of the students who helped or who did a lot of this work, especially Felix Schumann, of course. And I really want to thank the YEGs for having this genius idea of setting up this webinar series during those crazy times. It's always been a delight for me to kind of catch the webinar and feel a bit more in touch with the international community. And this is really great. I can imagine it's a lot of work for you to organize this thing and to keep this going. So thank you so much for making this possible.
Thank you very much, Anika. It was, a wonderful presentation and with different kind of cases. There are already some questions, so I think in order to be on time, we have to move on to the question part. So let's start with the first question, and says about what is the degree of uncertainty of the results obtained by these methods compared with the traditional ones? Depending what you're considering traditional ones.
It's a good question, because the traditional methods are also, they are also statistical methods. Maybe traditional methods would be going to the field and mapping landslides in the field. So I don't have any estimates about the uncertainty. Of course, to be able to do that, you would actually have to go back to the field with your model to check, for example, whether some of the areas that turned out highly susceptible but had no landslide in your inventory. So maybe you can go back to the field and check that. But of course, I cannot quantify now this kind of degree of uncertainty.
Okay. So next question is, what are the softwares or tools you usually use for training the model and generate the map? Do you recommend to use the machine learning tool in GIS software? I wonder whether using different tools to train and test the model will affect the model performance or not. For example, does using different tools, GIS, Python, R, to train the model matter?
Yeah, that's a really good question about the software. So we here actually use a very convenient software from IBM, because we also use this for teaching. And so we feel like the barrier for many students is really high if they first have to learn how to program for using tools like R or Python. So we use this like really software with this really convenient user interface. So the barrier for programming is just really low. So I actually have no experience in doing the training and the testing, for example, in different softwares, but I don't know if this is actually possible to transfer a model from one software to another to run the data through it. I don't have experience with that,
Okay.
but maybe I didn't catch the question right.
I mean, from my experience, it's completely independent. So if you're using a kind of set files or vector data, it depends on the transfer that you're doing and the datasets that it has been used. So it's not a matter of software. Let's move to the next question. Does the DEM of the case study represent the area before or after the occurrence of the failures in the inventory? If it's after, how we make sure that we do not turn it into a landslide detection model? Oh yeah, this is also a really good question. So in our case, the Rockfall inventory that we used, this was spanning like a longer time frame. So I guess the DEM was created at some point during this time. So, but I think the resolution of the DEM with 10 meters is maybe not enough to really detect a rockfall is maybe, let's say, 1 cubic meter or so. And I think the 10-meter DEM would not be enough to actually see the missing block in the cliff. So yeah, in this case, but in general, this is a really good question, because nowadays we also have like really high resolution DEMs. And then, this is what I also meant when I said, when we define our question, we really have to also look at the data we have. So sure, if we have like a high resolution DEM, then this will probably be a detection model if this is after all those landslides occurred, sure. How would you validate the reliability of model outputs in instances where there is significant under-representation or phenomenal circumstances that are atypical to existing datasets variables? Okay, I have to read that again. Yeah, it's more like how you validate your results and you assess the model outputs. It's from Zermatten. Yeah, so in areas where we have a significant underrepresentation, so what we usually do is we first do an explorative study where we use different balancing fraction or ratios, and then we just see how the models react. So we don't, for example, so of course at some point if you balance too much, you get a lot of false positives, for example. And then this is also, again, a little bit depending on what you want from the model. So if you don't want so many false positives, you should, for example, reduce the balancing. So I don't really understand what phenomenal circumstances. Phenomenal circumstances that are typical to existing datasets. Don't get it to help on that, to be honest. Probably we can move on, and that then we can define what we would like to outline. Next question is how to identify the landslide spot from the imagery data. Should it be done manually? Please suggest. I don't. Identify the landslide spot from the imagery data. Probably the inventory. How to create the inventory? This also depends on your imagery data, how the resolution is of this, and whether you want to map, for example, spots or points, or, for example, polygons. It's kind of... So, but of course, this was
this has been done manually for a long time, but also nowadays we have a lot of methods from remote sensing that we can actually use to do this automatically. So I think this is really exciting. I think the methodology for this automatic landslide mapping is just being developed right now. So I think in the next years, we will also have so much more data on landslide inventories that we can again feed into our machine learning models. So this is something that's also emerging right now.
Next question is, what is your opinion on why stakeholders are reluctant? Related to slide number 32.
Yeah, I think that, well, at least the people we interacted with in this project, for example, I think most of them, they are not trained with those methods. I mean, they are pretty new anyway. And so, yeah, a lot of like older people are, of course, not trained with this. So here, for example, we teach our students those methods, and we've also done this in Aachen. So the engineering geology students, they actually they get some training in those methods. And I think the generation that's currently being educated, they will definitely be trained in those methods. So I have a feeling that this would probably be something that would also change in the years to come when more young people also enter the geological surveys, for example. And yeah, so machine learning has this reputation of being just black box, and I think the people don't really trust in the models because it's really hard to understand them or to kind of reproduce what those models do. So of course, I think those are some of the reasons.
Yeah, and something that it should be outlined is that we have a lot of training data for inventory, so we should take advantage of that. So let's go to the last question. In case we use slope units instead of grid cells for landslide susceptibility modeling, how do we assign them values and its morphological parameters to each slope unit? I mean, how do you generalize their distribution to obtain a single value to assign the slope unit polygons?
Oh yeah, this this is also a question I'm thinking about a lot. So very good point. Yeah, so I think what is done in many studies is that you take only like descriptive statistical values for each slope unit. So for example, for the dam, you could use the mean and the range of the dam. For the slope angle, you would use the mean. For nominal data, such as the lithology, you could use the most frequent value, for example. But yeah, I think, so in my view, this is really difficult because this is a really an oversimplification kind of. And the whole point of machine learning is to use like really complex data sets where you can actually find interesting things. And by using this descriptive statistical values for each slope unit, you kind of blur all the information that was in the data before. So it's a little bit tricky. So what we often do, or what we try to do so far, is using the slope units to discretize the positives in the data set. So if there was a landslide on one slope unit, we say, okay, the whole slope unit could be affected by landslides because it has the same conditions. And then we use this as the positive inputs for the modeling. But the rest of the modeling we do on a grid cell basis. And we actually had some quite interesting outcomes with this compromise between slope units and grid cells. But there are also other like really geeky things, like Luigi Lombardo, for example. He did something with like Poisson point distributions to account for the variables within the slope units. So yeah, this is really cool stuff. But then again, I think this is maybe something we cannot convince someone working at a geological survey to use. So yeah.
Okay, I think we are a little bit over time. I think it's time to finish our session. I would like to thank all the attendees and, of course, our presenters, Professor Corominas and Dr. Braun. It was our pleasure. As committee, as Young Engineering Geologist Group, we will keep and continue our work for providing and sharing knowledge to different countries and different regions of the world. Once again, I would like to thank you. I would like to thank Dr. Braun, Dr. Corominas. Thank you all for being here. I don't know if you have something last to say, Professor Corominas or Dr. Braun.
Oh, thank you very much for this opportunity to share our thoughts, and also for the presentation of Anika, and it was very interesting. So until the next opportunity.
Hoping that we will have our chance to meet all together somewhere in the future in one non-virtual conference, let's say. So thank you all. It was our pleasure. Stay tuned for more actions from the e-YEG. Thank you all.
Okay, bye-bye.
Thank you so much. Bye.